In this video, we are going to be looking at mean, variance, and standard deviation of a binomial distribution. Please, before you continue, you can click down there on the subscribe button in case so that you can get notification for all of our classes. So let's move to the point here. We have the mean for a binomial distribution to be equal to NP. Now we should know that mean is the same thing as the expected value of x. Okay, we are getting there, we are coming to that. So your mean is NP, your N is the number of trials, and your P is the probability of success. So mean is NP. We are going to be seeing the proof soon. Then while variance is equal to NPQ. So your N, number of trials, your P is the probability of success, your Q is the probability of failure. Then standard deviation, like we know, is equal to the square root of variance, so square root of NPQ. Now let's see the proof. How did this formula came about? Okay, we have mean to be expected value of x, and if you remember, expected value of x, check our video on that, is equal to x times f of x, actually summation of x times f of x. You know, expected value of, let's say, x squared is equal to summation of x squared times f of x, and so on and so forth. So that's a general formula for expected value. So that is why we have this, okay? And f of x for binomial distribution is n combination x p raised to power x, then q raised to power n minus x, okay? But our n combination x here, we are using nx, we are putting enclosing it in a bracket this way, okay? So that's why we have this. So you have your x here and you have your f of x as this. Now remember that your n combination x means n factorial over n minus x factorial times x factorial, according to the definition for combination. Now from there we can, which is exactly what we have there. Now from there we can break this down. N factorial now becomes n times n factorial now becomes n times n minus 1 factorial. That breakdown is right, and your x factorial also becomes equal to x times x minus 1 factorial. That breakdown is right. That's exactly what we achieved here. Then your p raised to power x, now we want everything to be in terms of x minus 1, and because of that we can say that your p raised to power x is equal to p raised to power x minus 1, because we want everything to be in terms of minus 1. Okay, so we can add up minus 1 plus 1, okay? And minus 1 plus 1 is still 0, so it's still the same thing. So we can say this is p raised to power x minus 2 times p raised to, x minus 1, then times p raised to power 1, which is exactly what we have here, p to power x minus 1 times p. Now, conversely, we can also have this, that p raised to power x is equal to p raised to power x minus 2 times p raised to power 2 is still correct. We can also have p raised to power x equal to p raised to power x minus 3 times p raised to power 3 is still correct, depending on what, 3, depending on what we want to achieve. So let's continue there. Now, in the whole of this, NP here is a constant, so it can be brought outside our summation sign. They are constant, has nothing to do with the summation sign. Then your value of x here cancels x here. Okay, so at that point we have this left, which is n minus 1 factorial, over n minus x factorial times x minus 1 factorial. Then we have p raised to power x minus 1, q raised to power n minus x. And the whole of this is looking exactly like the binomial distribution. And the summation of a probability must be equal to 1. You know, a probability, binomial distribution is a probability distribution, and the summation of all must be equal to 1. And so NP times 1 gives us NP. Okay, now I want to show us why this is the same thing as that. So if we say now let n be equal to n minus 1, and let your x be equal to x minus 1. If you replace that here, you are going to get n factorial over n minus x factorial, then x factorial, p raised to power x, and q raised to power n minus x, which is exactly the binomial distribution. That is how we know. So, and so you can see that the mean of a binomial distribution is equal to NP. Now we continue there to the variance of x. Now the variance of x, like we know, is the expected value of x squared minus the expected value of x all squared. Now this expected value of x squared, we want to range it to be in terms of x minus 1. So we introduce this, which is plus x minus x, which is still 0, but we introduced it because we have a focus in mind. Okay, so if we factorize x now between these two, we are going to get x into x minus 1. Then we have plus x. Sorry, we have plus x. Okay, so at that point here, we get this. And now which we can separate as this exponential x into x minus 1 plus exponential x. That's according to the law of expectation. Now when you have expectation of a plus b, it's the same thing as the expected value of a plus the expected value of b. Okay, that's the reason for this separation here. Now we can take this, which is the expected value of x into x minus 1. It is the same thing as x into x minus 1, summation of x into x minus 1 times f of x, which is the definition for expected value, which is x into x minus 1 times f of x is the whole of this for a binomial distribution. Okay, so we move on to, that's what we have here, x into x minus 1. Then your n factorial, you can see that in this case here, we broke down n factorial to be n into n minus 1, then times n minus 2 factorial. We choose to stop here for a reason. Then the same thing with x factorial becomes x into x minus 1 and x minus 2 factorial, because we needed something to cancel out at the end of the day. Then you can see that your p raised to power x now is now replaced with p raised to power x minus 2 times p raised to power 2. That is how we got the whole of this. Now let's bring out the constants here. N minus 1 here is a constant, we bring it out. Then your p squared here is a constant, we bring them out outside the summation sign. So we are left with n minus 2 factorial, n minus x factorial, x minus 2 factorial, p raised to power x minus 2, q raised to power n minus x, which is also a binomial distribution. That is an arrangement for a binomial distribution, which is n combination, x. So the summation of all that is equal to 1. Summation of the total probability distribution is equal to 1. And that is how we got n into n minus 1 p squared. Okay, so coming back to our formula for variance, which is expected value of x squared minus expected value of x, which is expected value of x into x minus 1 plus expected value of x, then we have minus expected value of x all squared. Remember that this gave birth to this and this. Okay, then why this remains the same, remains this. Now we continue from there to see that our expected value of x into x minus 1, we just found out, is this n into n minus 1 p squared. Then expected value of x is what we've done before, which is the mean, np. Then the expected value of x all squared is np all squared. Okay, so if we open our bracket here, we are going to get n squared p squared minus np squared, opening the bracket, then plus np, then minus n squared p squared. When you open this bracket, you are going to get this n squared p squared. So you see here, n squared p squared cancels n squared p squared. So we are left with np minus np squared, okay, which is exactly what we have here. And when you factorize np, you are going to get 1 minus p, which is exactly what we have here. And 1 minus p is q. Remember, the probability of failure is equal to 1 minus the probability of success. So we have npq. So that is how we come about the formula for variance. So we can confidently say now that the variance of x is equal to npq. Wow, that's wonderful. Now let's see a question here. Okay, it says in 100 tosses of a fair coin, we have 100 tosses of a spare coin. The expected number of heads is, we are looking for the expected number of heads, and the variance is, so the total number of trial n is equal to 100. This is a binomial distribution. Okay, we have 100 trials, and we will need to find the expected value of heads. And for a particular coin, a single throw of coin, the probability of expecting of head is equal to 1 over 2. Okay, it's going to be 1 over 2 because that's what we expect. So we can now, that means our expected number of heads is EX is going to be NP as our formula, and your N here is 100 and your P here is 1 over 2, so that is going to give us 50. So that means the expected number of heads, or the expectation, is 50. Okay, now what is the variance? The variance, like we know, variance of x is equal to NPQ. Okay, so your N already, like we saw, is 100 times your P is 1 over 2, your Q is also 1 over 2. Probability of failure is 1 minus probability of success. So if the probability that the head shows up is half, it means that the probability that the head does not show up is also half. So, and this is going to give us 25. So the variance is equal to 25. Now we look at another example here, where we have, if the probability of a defective bolt is 0 0.1, so we said P is equal to 0 0.1. But I'd like us to note that it means that Q is equal to 0 0.9, 1 minus P. Okay, we're asked to find the mean and the standard deviation for the number of defective bolts in a total of 400 volts. So our N is 400 volts. Now our mean is going to be equal to NP. So where our N is 400 and our P is 0 0.1, okay? So that's going to be 40. So mean is 40. Remember, mean also means the expected value. So it is equal to 40. Now B says we should find the standard deviation. Let's find the variance first of all. The variance is NPQ for a binomial distribution. Okay, your N is 400, your P is 0 0.1, and your Q is 0 0.9. Okay, and that gives us 36. That's our variance. And remember, our standard deviation is the square root of variance. So we have square root of 36, which is equal to 6. So that means our standard deviation is equal to 6. Thank you for joining us in this very video. Please don't forget to click the subscribe button in case you have not done that, to get more of our classes. Thank you very much. I wish you the best.